The paper proposes two novel approaches for processing multidimensional graph signals in the linear canonical transform domain. The first approach is the two-dimensional graph linear canonical transform based on the central discrete dilated Hermite function, 2D CDDHFs-GLCT, and the second is based on chirp multiplication-chirp convolution-chirp multiplication decomposition, 2D CM-CC-CM-GLCT. These methods are then extended to M-D CDDHFs-GLCT and M-D CM-CC-CM-GLCT for higher dimensional signals. A comparative analysis shows that M-D CM-CC-CM-GLCT has significantly reduced computational complexity compared to M-D CDDHFs-GLCT. Simulation results demonstrate comparable additivity to M-D CDDHFs-GLCT and better reversibility for M-D CM-CC-CM-GLCT. The authors apply M-D GLCT to data compression, showcasing its application advantages. Experimental results highlight the superiority of M-D GLCT in algorithm design and implementation for data compression. This work is supported by the National Natural Science Foundation of China and other key institutions, underscoring the importance of this research in the field of signal processing. Graph signal processing has emerged as a crucial technology for handling complex high-dimensional data with irregular topological structures, deviating from the conventional timespace domain. This technology has found applications in various domains, including radar surveillance, biomedicine, and image processing. To study graph signals, it is essential to extend traditional signal processing concepts, such as graph signal transform, convolution, filtering, shifting, and modulation, to the graph signal domain. These concepts establish a comprehensive theoretical system for graph signal processing. There are two primary construction frameworks for graph signal processing: spectral and algebraic methods. The spectral method, based on the Laplace matrix, intuitively analyzes graph structure using spectrogram theory. Specifically, the graph Fourier transform, GFT, is defined by the eigenvector of the Laplacian matrix, and the corresponding spectrum is represented by eigenvalues. However, this method is limited to undirected graphs, as the Laplacian matrix must be symmetric and positive semidefinite. In contrast, the algebraic method, derived from discrete signal processing on graphs, analyzes graph structure characteristics using algebraic methods. The GFT is defined by the eigenvector of the adjacency matrix, and the corresponding spectrum is represented by eigenvalues. This method is applicable to any graph, as the adjacency matrix may not be symmetric. Despite the similarities with the classical Fourier transform, GFT may not adequately address certain mathematical challenges in practical applications, prompting the introduction of new transform methods, such as the linear canonical transform, to overcome these limitations. The traditional graph Fourier transform, GFT, struggles to accurately represent multidimensional graph signals, motivating the development of the multidimensional GFT, M-D GFT. This novel approach rearranges the 1D spectrum into an M-D frequency domain, enabling a more comprehensive analysis of complex graph signals. To further enhance local graph signal features, the fractional Fourier transform, FRFT, is incorporated, allowing signal representation in the fractional domain. However, both GFT and FRFT face challenges in representing M-D graph signals, particularly for graphs with numerous nodes. To address these limitations, the concept of multidimensional graph FRFT, M-D GFRFT, is proposed. By avoiding the binary spectrum of 1D GFRFT, M-D GFRFT reduces computational complexity and provides a more effective representation of M-D graph signals. Another promising approach is the linear canonical transform, LCT, which expands rotation to affine transformation, enabling non-band-limited signals to become band-limited. This property makes LCT an attractive tool for graph signal processing. To leverage the strengths of LCT in the graph signal processing domain, the concept of graph LCT is introduced, based on central discrete dilated Hermite functions. This innovative approach has the potential to overcome the limitations of traditional graph signal processing techniques, providing a more accurate and efficient framework for analyzing complex graph signals. Future work involves extending LCT to graph signals processing, enabling the development of more sophisticated graph signal analysis techniques. The paper introduces two novel multi-dimensional graph linear canonical transforms, M-D GLCT, for the analysis of multi-dimensional graph signals. These transforms are based on Cartesian product decomposition of discrete Hankel functions, CDDHFs, and Cartesian product decomposition, CM-CC-CM, respectively. They offer enhanced flexibility and freedom compared to the multidimensional graph Fourier transform, M-D GFT, and multidimensional graph fractional Fourier transform, M-D GFRFT, providing a more detailed frequency analysis of multidimensional graph signals. The M-D CDDHFs-GLCT and M-D CM-CC-CM-GLCT are independent of the sampling periods and do not require oversampling operations. In terms of computational complexity, M-D CM-CC-CM-GLCT has lower complexity than M-D CDDHFs-GLCT, making it more efficient in practical applications. Both transforms achieve additivity, with M-D CM-CC-CM-GLCT showing better reversibility, which is beneficial for applications such as coding and decoding. The paper also applies M-D GLCT for data compression, demonstrating its advantages over M-D GFRFT. Experimental results indicate that M-D GLCT achieves closer fidelity to the original data at equivalent compression ratios, with smaller errors. This research significantly contributes to the development of novel signal processing techniques and has potential applications in various fields. The paper begins by introducing the concept of a graph G, V, E, A, with nodes V, edges E, and weighted adjacency matrix A. It then defines the Cartesian product graph G1 hollow square G2 as a graph with vertex set V1 times V2, where V1 and V2 are sets of nodes from two different graphs G1 and G2. The edge set E of the Cartesian product graph satisfies a specific condition. If there exists an edge between nodes I1, I2, and J1, J2, then either there is an edge between nodes I1 and J1 in G1 and I2 equals J2, or there is an edge between nodes I2 and J2 in G2 and I1 equals J1. The paper also explains that for a factor graph Gn with degree matrix Dn and Laplacian matrix lane, the adjacency matrix, degree matrix, and Laplacian matrix of G1 hollow square G2 can be expressed as A1 circled plus A2, D1 circled plus D2, and L1 circled plus L2, respectively, using the Kronecker sum operator circled plus. This operator is defined as a circled plus B equals A circled times in plus IM circled times B for matrices A and B of sizes M times M and N times N, wherein is the identity matrix of size N. This section provides a foundation for understanding the two-dimensional graph operations that will be used in the subsequent sections of the paper to define and extend the two-dimensional graph Laplace and cosine transforms. In graph signal processing, the graph Fourier transform, GFT, is a fundamental concept, commonly defined by decomposing a general graph shift operator, GSO, Zn. The graph Laplacian, lane equals DNN, and the adjacency, Zn equals N, are typically considered. The Jordan decomposition of Zn yields Zn equals VZJV-1, enabling the definition of the GFT matrix as F_Gn equals V-1. For undirected real-weighted graphs, the GSO-Zn can be decomposed into Zn equals VZ lambda V-H, where lambda is a diagonal matrix composed of eigenvalues, lambda I, Vz is a matrix composed of eigenvectors, UI, and V-H is the inverse matrix of Vz. The eigenvalues and eigenvectors contain information about the graph structure signals, with larger eigenvalues corresponding to higher frequency information and more violent fluctuations, and smaller eigenvalues corresponding to lower frequency information and smoother characteristics. The 1D GFT of a signal x on a graph G is defined as O_1D GFT, x, equals F_GNX equals V-HZNX, where f_gn is the graph Fourier transform matrix and O_1D GFT denotes the 1D GFT operator. This decomposition represents the signal x as a vector x equals x0, x1, xn1, t, comprising its frequency components. For signals on Cartesian product graphs G1 hollow square G2, the 2D GFT is defined. The GSO matrix Zn of graph G is decomposed as Zn equals Vz lambda V h for n equals 1, 2. The 2D GFT of a signal x. V1 times V2 right pointing arrow r is defined as x, lambda 1, k1, lambda 2, k2, equals underscore, I1 equals 0, n11. Underscore, I2 equals 0, n21. Vz1, I1, lambda 1, k1, Vz2, I2, lambda 2, k2, x, I1, I2, where k1 equals 0, n11 and k2 equals 0, n21. The inverse 2D GFT is defined as x, I1, I2, equals underscore, k1 equals 0, n11. Underscore, k2 equals 0, n21, Vz1, I1, lambda 1, k1, Vz2, I2, lambda 2, k2, x, lambda 1, k1, lambda 2, k2. The two-dimensional graph Fourier transform, 2D GFT, is a matrix-matrix multiplication chain, as shown in equation 5, where X is an n1xn2 matrix and X is the transformed matrix. Its inverse can be represented similarly, as shown in equation 6. The vector formulation of the 2D GFT is a Kronecker product of two graph Fourier transform matrices, as shown in equation 7, where X is a vectorized version of the matrix X and X is the transformed vector. The inverse of the 2D GFT in the vector formulation is shown in equation 8. The paper introduces the concept of the two-dimensional graph fractional Fourier transform, 2D GFRFT. The Jordan decomposition of the graph Fourier transform matrix FGN is obtained as FGN equals VFN JFN 1, where VFN and JFN are the eigenvectors and eigenvalues of FGN, respectively. The unidimensional graph fractional Fourier transform, 1D GFRFT, of signal x on a graph Gn is defined as decomposing the graph shift operator, GSO, Z as O alpha 1D GFRFT, x, equals F alpha GNX equals VFNJ alpha FNV 1, FNX, where alpha is a parameter in the range 0, 1. The two-dimensional graph fractional Fourier transform, 2D GFRFT, of signal x on a Cartesian product graph G1 hollow square G2 is defined as decomposing the GSOs Z1 and Z2 as O alpha 2D GFRFT, x, equals FG2 circled times FG1, alpha x equals VF2 circled times VF1, JF2 circled times JF1, alpha V 1. F2 circled times V 1. F1x, where x is a vectorized version of the matrix X. In the realm of graph signal processing, two key transformations are pivotal for understanding and manipulating data on graphs: the two-dimensional graph chirp multiplication and the two-dimensional graph scaling transform. The graph chirp multiplication matrix is defined by decomposing the graph shift operator, which in turn is achieved through the chirp Fourier transform on graphs. This decomposition involves breaking down the graph shift operators Z1 and Z2 to define the two-dimensional graph chirp multiplication. The graph scaling transform, on the other hand, extends the concept of shift to general graph signals. It represents relational dependencies between data through arbitrary graphs. The transformation result is given by the product of the input signal and the relation matrix of the graph. These transformations are essential for analyzing and processing graph-structured data, allowing researchers to uncover insights and patterns within complex networks. A 1D graph scaling transform is a decomposition of the graph shift operator, GSO, into its eigenvectors and eigenvalues. This concept is extended to 2D graphs by utilizing the Cartesian product graph structure. The 2D graph scaling transform is defined by decomposing the GSOs of the constituent graphs and applying them to the signal in a specific order. Furthermore, the 2D graph linear canonical transform, GLCT, is introduced as an extension of the 1D GLCT to Cartesian product graphs. The implementation algorithms for 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT are discussed, focusing on the additivity of 2D GLCT and the decomposition of the parameter matrix into 3 or 5 matrices. These basic discrete operations have been previously defined. The parameter matrix M of 2D GLCT is a 4x4 transform matrix, also known as the ABCD matrix, consisting of 2x2 quantity matrices A, B, C, and D. This matrix representation enables efficient computation of the 2D GLCT, which is essential for signal processing on 2D graph structures. The decomposition of the parameter matrix into smaller matrices facilitates the implementation of the 2D GLCT algorithm, making it more computationally efficient. In the context of the 2D generalized linear canonical transform, 2D GLCT, parameters A, B, C, and D are defined as matrices with specific properties. These parameters satisfy certain conditions, such as add BC equals 1, and encompass various special cases including the 2D GFT, 2D GFRFT, 2D graph CM, and 2D graph scaling transform. For instance, the 2D GFT has a parameter matrix given by M equals 0, I, 0, where I is the identity matrix. Similarly, the 2D GFRFT has a parameter matrix M equals phi, psi, phi, where phi and psi are matrices defined by cosine and sine functions of a parameter alpha. The 2D graph CM and 2D graph scaling transform also have their respective parameter matrices M equals I, 0, G, I, and M equals K, 0, 0, K caret 1, where G and K are matrices defined by parameters xi and sigma. KOC et al. Proposed a fast algorithm for calculating 2D GLCT, which is based on CDDHFs decomposition. This decomposition is expressed as a product of 3 matrices, each corresponding to a different transform: 2D graph CM, 2D graph scaling transform, and 2D GFRFT. The relationship between the parameters of these transforms and the original parameters, A, B, C, D, is also provided, showing how they can be derived from one another. The decomposition of the 2D graph-based linear canonical transform, GLCT, into its constituent components involves a combination of 2D graph-based continuous morphological transform, GCM, 2D graph-based scaling transform, GST, and 2D generalized fractional Fourier transform, GFRFT. The 2D GLCT is defined as the CDDHFs-GLCT, which decomposes the graph shift operators, GSOs, Z1 and Z2 into their corresponding components. This decomposition is a special case of the Iwasawa decomposition of symplectic matrices. The realization of the 2D CDDHFs-GLCT is achieved through the combination of 2D graph CM, 2D graph scaling transform, and 2D GFRFT, as expressed in equation 23. The page also introduces the 2D CM-CC-CM-GLCT, which is based on the CM-CC-CM decomposition of the 2D parameter matrix. This decomposition is expressed in equation 24, and is applicable when the determinant of the matrix B is non-zero. The CM-CC-CM decomposition enables the calculation of 2D GLCT without scaling operations, thereby reducing interpolation errors. The 2D parameter matrix decomposition is further decomposed into its constituent components, including 2D graph CM with chirp rates xi1 and xi3, and 2D graph CC with parameter B. The 2D graph CC is decomposed into its constituent components, as expressed in equation 25, which includes 2D graph CM with chirp rate sheet 2 and 2D graph CM with chirp rate B. This decomposition enables the realization of the 2D CM-CC-CM-GLCT, which is composed entirely of 2D GFT, 2D IGFT, and 2D graph CM. The paper presents a novel approach to understanding the dynamics of complex systems through the lens of nonlinear differential equations. It delves into the intricacies of chaotic behavior, shedding light on the interplay between initial conditions and system parameters. The authors employ the Lorenz model as a paradigmatic example, demonstrating how minute variations in initial conditions can lead to drastically different outcomes. This sensitivity to initial conditions is a hallmark of chaotic systems, underscoring the inherent unpredictability that pervades these systems. A key finding of this research lies in the discovery of novel attractors within the Lorenz system. These attractors, which represent the long-term behavior of the system, exhibit intricate patterns that defy traditional notions of periodicity and stability. The study also explores the role of bifurcations in shaping the system's behavior. Bifurcations are critical points at which the system undergoes a qualitative change, transitioning from one type of behavior to another. The authors show how these bifurcations can be harnessed to control the system's dynamics, offering potential applications in fields such as engineering and physics. In conclusion, this research contributes significantly to our understanding of complex systems, highlighting the delicate balance between order and chaos. It underscores the importance of considering both the initial conditions and system parameters when attempting to predict the behavior of such systems. The multidimensional signal processing context is explored through the relationship between various parameters, starting with the definition of the multidimensional graph linear canonical transform, M-D GLCT, and its parameters, A, B, C, D. This is followed by the definition of the M-D CM-CC-CM-GLCT and its parameters. Equations detail transformations and relationships between these parameters, highlighting the significance of chirp rate, scaling factor, and fractional transform order in the M-D GLCT. The M-D CM-CC-CM-GLCT is defined for a M-D signal X on a Cartesian product graph G1 hollow square GM when DETB equals 0. This definition is presented in equations 38 and 39, where the M-D CM-CC-CM-GLCT is decomposed into the product of generalized Stockwell transforms and inverse Fourier transforms. The phase differences between the Fourier transform and the linear canonical transform are denoted by square root j and square root j, respectively. The parameters Xi4, Xi5, Xi6, and Xi7, Xi8, Xi9 are related to the parameters A, B, C, and D through equations 40 and 41, respectively. These relationships are essential in understanding the properties of the M-D CM-CC-CM-GLCT. The M-D CM-CC-CM-GLCT is compared to the M-D CDDHFs-GLCT in terms of computational complexity, additivity, and reversibility. The 2D case is taken as an example to facilitate the comparative discussion. The computational complexity of the 2D CDDHFs-GLCT is analyzed, and it is shown that each of the real matrices Vs1 and V1F1 generates 2n2 real multiplications, while each of the complex diagonal matrices J∈F1 and J∈F1 generates n1 complex multiplications. Similarly, each of the real matrices Vs2 and V1F2 generates 2n2 squared real multiplications, and each of the complex diagonal matrices J∈F2 and J∈F2 generates n2 complex multiplications. A comprehensive comparison of the computational complexities of two-dimensional CDDHFs-GLCT and 2D CM-CC-CM-GLCT is presented. The complexities of both methods are broken down in Table 1, highlighting the number of real multiplications required for each. The 2D CDDHFs-GLCT method involves matrix multiplication and eigendecomposition, resulting in a complexity of 4, n2, plus 8, n1 plus n2, real multiplications. In contrast, the 2D CM-CC-CM-GLCT method has two cases. Det B equals 0 and det B equals 0. For det B equals 0, the method requires 3 2D graph CMs, 2D GFT, and 2D IGFT, resulting in a complexity of 12, n1 plus n2, plus 4, n1 log 2 n1 plus n2 log 2 n2, real multiplications. For det B equals 0, the method requires an additional 2D GFT, or 2D IGFT, increasing the complexity to 12, n1 plus n2, plus 6, n1 log 2 n1 plus n2 log 2 n2, real multiplications. The additivity property of the 2D GLCT is also discussed, which is expressed as matrix multiplication. This property is compared for 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT using the normalized mean squared error (NMSE) metric. The NMSE is calculated as the difference between the 2D GLCT of the product of two matrices and the product of the 2D GLCT of each matrix. Simulations are conducted on 4 types of 2D graph signals, and the results are presented in Figure 1. The NMSE is calculated using equation 43, which compares the 2D GLCT of the product of two matrices with the product of the 2D GLCT of each matrix. The comparison of two-dimensional, 2D, graph signal transforms, specifically the 2D CDDHFs-GLCT and the 2D CM-CC-CM-GLCT, begins with the definition of the additivity property, a measure of how well they preserve the sum of two graph signals. 4 examples of graph signals, x1 to x4, and their corresponding graphs, g1 to g4, are presented, each with different numbers of vertices and structures. The normalized mean square error, NMSE, is calculated for these signals using both transforms, showing that the 2D CM-CC-CM-GLCT has similar performance to the 2D CDDHFs-GLCT in terms of additivity. The investigation of the reversibility property, which measures how accurately the original signal can be recovered from its transformed version, follows. The NMSE for reversibility is calculated, revealing that the 2D CM-CC-CM-GLCT outperforms the 2D CDDHFs-GLCT in this regard. The authors summarize their findings in Table 4, comparing the two transforms across various properties such as additivity, reversibility, and computational complexity. This research contributes to the development of more efficient and accurate graph signal processing techniques. In the realm of graph signal processing, the authors conduct a comparative analysis of two methodologies, 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT, focusing on their performance in additivity running averages. 4 graph signals, x1 to x4, are visualized in Figure 1, showcasing distinct structures. These signals are then subjected to additivity running averages calculation using the aforementioned methods, which are rooted in graph convolutional neural networks, GCNNs, and leverage graph Laplacian convolution. The 2D CDDHFs-GLCT method employs a GCNN with a continuous domain dynamic harmonic filter, CDDHFs, and a graph Laplacian convolutional transform, GLCT. In contrast, the 2D CM-CC-CM-GLCT method utilizes a GCNN with a complex-valued mixing matrix, CM, a circulant matrix, CC, and a GLCT. The results, tabulated in Table 2, demonstrate that both methods produce additivity running averages with similar orders of magnitude, specifically on the order of E-31. Notably, the 2D CDDHFs-GLCT method yields additivity running averages of 4.9799, 11.4810, 3.9862, and 5.9608 for x1, x2, x3, and x4, respectively. In comparison, the 2D CM-CC-CM-GLCT method produces additivity running averages of 4.9398, 11.4900, 4.0500, and 5.9680 for the same graph signals. This comparative analysis provides valuable insights into the performance of these graph signal processing methods, which can be instrumental in various applications such as graph-based signal processing and machine learning. The authors empirically evaluate the additivity property of the 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT methods, showcasing the superior performance of the latter. Figure 2 illustrates the normalized mean square errors, NMSEs, of the additivity property for 50 different sets of M1 and M2, demonstrating the 2D CM-CC-CM-GLCT method's improved ability to preserve additivity. The NMSEs of the 2D CM-CC-CM-GLCT method are consistently lower than those of the 2D CDDHFs-GLCT method. Table 3 compares the 1000 reversibility running averages for both methods, listing the critical components x1, x2, x3, and x4. Notably, the values obtained using the 2D CM-CC-CM-GLCT method are significantly lower than those obtained using the 2D CDDHFs-GLCT method, with an order of magnitude of E-30, indicating superior reversibility properties. The evaluation is grounded in the mathematical framework established earlier, where additivity and reversibility are essential conditions for ensuring the validity of the proposed methods. By demonstrating the 2D CM-CC-CM-GLCT method's superior performance in preserving these properties, the authors provide strong empirical evidence for its effectiveness. This evaluation is significant for the broader field of machine learning and signal processing, where developing methods that accurately preserve additivity and reversibility is crucial. The authors' findings contribute to the advancement of this field by providing a novel approach that outperforms existing methods, highlighting the potential of the 2D CM-CC-CM-GLCT method for future applications. The analysis of normalized mean square errors, NMSEs, for the reversibility property across various sets of M, as depicted in Figure 3, is crucial for evaluating the performance of different methods. Table 4 compares the 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT, highlighting their complexity, additivity, and reversibility properties. The 2D CDDHFs-GLCT exhibits a higher complexity but better reversibility compared to the 2D CM-CC-CM-GLCT, demonstrating the trade-offs between computational complexity and performance in the context of the research. In signal processing, efficient signal representation is crucial for domains such as storage, compression, and transmission. This section explores the application of the 2D CM-CC-CM-GLCT framework in data compression, comparing it with M-D GFRFT to demonstrate its better compression effect. The process involves calculating the 2D CM-CC-CM-GLCT of a signal using equation 26, ranking coefficients by their absolute values, and then compressing the signal by reserving the maximum amplitude coefficient and setting the rest to 0. To evaluate the compression loss, three quantities are used: relative error, RE, normalized root mean square, NRMS, and correlation coefficient, CC. These metrics are designed to measure the error between the compressed and original signals, with smaller values indicating better compression, and the correlation coefficient assessing compression efficiency. The table on page 21 of the research paper presents the reconstruction error, RE, of 2D GFRFT and 2D CM-CC-CM-GLCT under different compression ratios, gamma. The results indicate that the optimal rotation angle parameter for 2D GFRFT is 1, reducing it to 2D GFT. In contrast, 2D CM-CC-CM-GLCT offers a better transformation basis and produces smaller errors. The specific parameters used for 2D CM-CC-CM-GLCT are detailed in Table 5, with a range of values for A, B, C, and D depending on the compression ratio. Compared to M-D GFRFT, M-D CM-CC-CM-GLCT can preserve more data details and structural information during compression, resulting in smaller differences between compressed and original data. This suggests that M-D CM-CC-CM-GLCT can effectively maintain the original data characteristics without significant distortion or errors introduced by compression. The parameter selection process involves iterative refinement, with adjustments in linear regularization parameters to achieve better compression. The paper concludes by proposing a multidimensional graph signal processing method that preserves the dimension information of multidimensional graphs. It introduces two-dimensional graph linear canonical transforms, specifically 2D CDDHFs-GLCT and 2D CM-CC-CM-GLCT, derived from CDDHFs decomposition and CM-CC-CM decomposition. These transforms are then extended to multidimensional, resulting in M-D CDDHFs-GLCT and M-D CM-CC-CM-GLCT. The results of the 2D GFRFT and 2D CM-CC-CM-GLCT algorithms under different compression parameters and rotation angles are discussed. Figure 4 illustrates the Re, NRMS, and CC of 2D GFRFT with varying rotation angles and compression parameters. Table 6 compares the NRMS of both algorithms for different compression ratios, highlighting the optimal rotation angles for each. The results show that 2D GFRFT generally outperforms 2D CM-CC-CM-GLCT in terms of NRMS, especially at higher compression ratios. The selected parameters for 2D CM-CC-CM-GLCT are detailed, demonstrating the algorithm's adaptability to different compression settings. This data provides insights into the performance of these algorithms under various conditions, crucial for optimizing image compression techniques. The comparison between the 2D GFRFT and the 2D CM-CC-CM-GLCT with different compression parameters gamma is presented in Figure 5 and Table 7. Both methods exhibit high compression performance, with the 2D GFRFT achieving a CC of 94.31% at gamma equals 0.1 and the 2D CM-CC-CM-GLCT achieving a CC of 95.50% under the same conditions. As gamma increases, both methods improve in performance, with the 2D GFRFT reaching a CC of 99.87% at gamma equals 0.9 and the 2D CM-CC-CM-GLCT reaching a CC of 99.95%. The optimal rotation angle alpha for the 2D GFRFT is consistently set at 1, while the parameters for the 2D CM-CC-CM-GLCT vary with different gamma values. This figure and table demonstrate the effectiveness of both methods in compressing images while maintaining quality. The research paper compares two algorithms, M-D CM-CC-CM-GLCT and M-D CDDHFs-GLCT, analyzing their computational complexity, additivity, and reversibility. Theoretical analysis indicates that M-D CM-CC-CM-GLCT has reduced computational complexity compared to M-D CDDHFs-GLCT. Simulation results show comparable additivity between the two algorithms, with M-D CM-CC-CM-GLCT exhibiting better reversibility. The paper also applies M-D GLCT to data compression, demonstrating its advantages. Experiments reveal that M-D GLCT achieves closer fidelity to the original data at the same compression ratio compared to M-D GFRFT, highlighting the superiority of M-D GLCT in algorithm design and implementation for data compression. In the realm of graph signal processing, a plethora of research has been conducted, as evidenced by the author's comprehensive literature review. Low-pass graph signal processing, with its various applications, has been extensively explored. 8. Distributed nonlinear polynomial graph filters have also been developed, offering new avenues for graph signal processing. 9. Moreover, the multidimensional graph Fourier transform has been investigated, providing a powerful tool for analyzing graph-structured data. 10. Forecasting multidimensional processes over graphs has been another area of focus, with researchers proposing innovative methods for predicting complex graph signals. 11. Sampling theory for graph signals on product graphs has been studied, shedding light on the optimal sampling strategies for these signals. 12. The fractional Fourier transform on graphs has been explored, enabling the analysis of graph signals in the fractional Fourier domain. 13. Recent advancements in graph signal processing include the development of fractional spectral graph wavelets, which offer a flexible framework for graph signal analysis. 14. The windowed fractional Fourier transform on graphs has also been proposed, allowing for the analysis of graph signals with varying frequencies. 15. Furthermore, the joint time vertex fractional Fourier transform has been introduced, facilitating the analysis of graph signals with both temporal and spatial dimensions. 16. The multi-dimensional graph fractional Fourier transform has also been developed, enabling the analysis of high-dimensional graph signals. 17. Lastly, the authors acknowledge the significance of the sparse discrete linear canonical transform and its diverse applications, which have expanded the toolkit for graph signal processing. 18. The authors provide a comprehensive review of the linear canonical transform, LCT, and its applications in signal processing, image analysis, and graph signal processing. The LCT is a powerful tool for signal analysis and has been extensively studied in various fields. Its discrete version has been explored for signal processing on graphs and digital signal processing in 19 and 22, respectively. Applications of the LCT to digital image processing and modeling circulating cavity fields are demonstrated in 20 and 21. Eigenfunctions of the LCT, fundamental to understanding the transform, are studied in 23. The chirp multiplication technique, closely related to the LCT, is used in 24 for wideband swept frequency sources in high-resolution imaging. A novel approach for graph signal processing, the graph LCT based on CM-CC-CM decomposition, is proposed in 25. Relevant concepts from graph theory, such as the Cartesian product of graphs, 26, and learning product graphs from multi-domain signals, 27, are also reviewed. Efficient computation of two-dimensional non-separable quadratic phase integrals, essential for implementing the LCT, is discussed in 28. This literature review underscores the significance of the LCT across various fields and its potential applications in signal processing, image analysis, and graph signal processing. The authors provide a thorough overview of existing research, laying the groundwork for further exploration of the LCT and its variants. The application of mathematical decompositions in signal processing and algebra is a pivotal concept that has garnered significant attention among researchers. This page delves into the intricacies of these decompositions, exploring their role in breaking down complex signals and algebraic structures into more manageable components. In signal processing, mathematical decompositions are employed to separate a signal into its constituent parts, each representing different aspects such as frequency components or time segments. This decomposition facilitates the analysis and manipulation of signals, allowing for tasks like filtering, compression, and feature extraction. For instance, the Fourier transform is a well-known decomposition technique used to break down a signal into its constituent frequencies. In algebra, mathematical decompositions are used to simplify complex algebraic expressions and equations. These decompositions can reveal underlying structures and patterns within the algebraic objects, aiding in solving equations, factoring polynomials, and computing eigenvalues. The Jordan decomposition, for example, is a technique used to diagonalize matrices, which is crucial in various applications including linear transformations and Markov chains. These decompositions not only provide insights into the nature of the signals and algebraic structures but also pave the way for novel algorithms and methodologies. They enable researchers to tackle complex problems more efficiently, leading to advancements in fields such as audio processing, image analysis, and quantum computing. However, it is essential to note that these decompositions are not without limitations. They often rely on certain assumptions about the nature of the signals or algebraic structures, and their efficacy can be influenced by factors like noise or numerical instability. Furthermore, the choice of decomposition technique can significantly impact the outcome, underscoring the importance of careful consideration and validation. In conclusion, mathematical decompositions play a vital role in signal processing and algebra, offering powerful tools for analyzing and manipulating complex objects. As research continues to evolve, the development of new decomposition techniques and their applications will remain a crucial area of study, driving innovation and progress in various fields.